So it's time to do a little soldering. Let's get this projects, plural, completed. This is a clone of an old HD1416 code practice oscillator. I first built one of these from the actual Heathkit in 1978, I believe it was. And then I built a clone of it in about 1982 for another ham radio friend, local, who wanted to give a code practice oscillator to a friend of his, hopefully inspiring the young fella to take up ham radio. Don't know if he ever did or not, as the friend has now been deceased for about 20 years, I would say. So there's that one, my third one, and then there's this board, which I'll do in another video. And then there's this one, which, as you can see, didn't get etched. Well, the process didn't take very well. I think I probably didn't have the toner set heavy enough, and so I said, to heck with it, I'll just draw it out with KiCad and have it commercially made. So that's what I've done, just waiting for the order to come in. I wanted to do this one first and then do the other two, but it didn't work out that way. So let's get going. Like all of my Heathkit projects, since I'm going to mimic the manual, I'll start off with resistors. So, last wires are hooked up. Let's plug in a battery and see what happens, shall we? And
it works. But I would have been highly, highly embarrassed if it hadn't. After all, this is such a simple circuit. Speaking of which, this is the schematic diagram for the HD1416. I'm going to ignore this portion of the circuit over here. It's just a Class A audio amplifier fed through a volume control. I'm sure there is a description of a Class A amp on the net somewhere, probably lots of them. But let me know if you would like me to cover the amplifier section. You'll see that this circuit is listed on the diagram as a multivibrator. But what kind? There are three: astable, monostable, and lastly, bistable. This is an astable multivibrator. If you search the net for astable multivibrator, you are likely to see something that looks like this. Now, it may not seem like it, but this schematic diagram is the same as our HD1416 schematic. It's just that the components are shifted from side to side on the diagram. This resistor and capacitor move to the left, with the capacitor moving up a bit, and the same thing for these moving to the right. If you look at the two diagrams and concentrate, you'll see that they are actually the same and that they function exactly the same. Now, in a standard astable multivibrator, which is pretty much what we have here with one exception, the components labeled R1 and R5 would be exactly the same value, either 10K or 5.6K. And then the resistors labeled R2, R3, and R4 would also be all the same value. You would actually normally just have two resistors of either 220K or 568K. And also C2 and C3 would be the same value, but they're not. Let's talk about how the circuit works. When the key is pressed, 9 volts from our battery is applied here. With a circuit like this, even though we use the same transistors from the same batch possibly, there will be slightly different electrical characteristics between them. Manufacturing is not a perfect process. When the voltage is applied, one transistor will always start conducting before the other. From a state of having been completely off, let's assume that Q1 starts conducting first. With Q1 conducting, the base is biased to on, the collector will be at or close to ground potential, and the left-hand plate of C3 will also be at ground potential. Because Q2 is not biased on, its collector, which is our output, will be at supply voltage level, so it will be high or on. C3 is uncharged at the moment with its plates at the same potential. But C3 begins to charge via the combination of R3 and R4. Its right-hand plate becomes increasingly more positive until it reaches about plus 0.7 volts. Q2 will then begin to conduct, causing a voltage drop across R5, and our output at the collector of Q2 drops to ground potential, which we call low or off. Now the right-hand plate of C2 drops to ground as well, taking the left-hand plate with it, which causes the voltage on the base of Q1 to go substantially negative, biasing Q1 off. Now with Q1 not conducting, the collector goes high on, and C3 now passes the collector voltage to the base of Q2, which is now turned fully on. This new state does not last long. C2 begins charging via R2, and once the left-hand plate reaches plus 0.7 volts, Q1 is biased on, and we return to the first state of the circuit with Q1 on and Q2 off. This back and forth process will continue until the key is released, at which point the entire circuit turns off. This creates what is more or less a square wave on the collector of Q2, which is passed on to a pair of headphones or to the amplifier circuit through a volume potentiometer, where we hear the square wave as a tone. But the collector of Q1 also turns off and on, doesn't it? What does that look like? Well, it's also a square wave, but it's the exact opposite of the output of Q2. High when Q2 is low, and low when Q2 is high. Let's demonstrate this with a scope. I have a scope probe on the collector of each transistor. As you can see, there are two square waves, the exact opposite of each other as described. But what does the trimmer pot do? It varies the width or frequency of the output pulse like this, where we can get a tone that matches what we would like it to be. One last thing. This portion of the circuit around the key and battery, and also this connection labeled ST, what is it? First of all, the connection labeled ST. The ST refers to side tone. Most modern ham transceivers, when you use Morse code, CW, when you press the key down, you hear a tone in the headphones or in the speaker. This is called side tone. It makes it easier to time your code rather than just having to rely on the sound of the clicks of the key alone. However, most older transmitters and transceivers didn't have this feature. Here are a couple of examples. I have used both of these transmitters, by the way, but the code practice oscillator could be used to key the transmitter through the ST connection, giving a nice side tone in the speaker while you transmit. A simplified explanation for the diode is that it's there to protect the rest of the code practice oscillator circuit from back voltages from the transmitter. Hope you enjoyed this video. I started it 3 years ago with the PCB etching videos and finally got around to finishing it. If you have any questions, let me know. Now.The.